Hello everyone, we'll start with preparation methods of ether. After that, there will be physical properties of ethers and chemical properties of ethers and some related problems. So the method that we are going to use for the formation of ether is bimolecular dehydration of alcohol. So from the name you can understand, as we are saying bimolecular, that means two molecules of alcohol we will take and we will get ROR. So you can write ROH, one ROH molecule in this way, another alcohol molecule, and if you remove water molecule H and OH, ultimately you are getting ROR. So this is the bimolecular dehydration. Why we are calling it dehydration? Because here water molecule is removed, so that is why it is dehydration. Fine. Now actual example, if you take, suppose you have taken two molecules of methyl alcohol, then in presence of H2SO4 and 140 degrees centigrade we are getting dimethyl ether, and obviously as it is dehydration there will be one water molecule. And if you have started with two molecules of ethyl alcohol, then under same condition it will produce diethyl ether. Fine. In practice, however, this bimolecular dehydration for the formation of ether, it will compete with unimolecular dehydration to give an alkene. Fine. So when we are saying unimolecular, that means from a single molecule of alcohol there will be dehydration. One water molecule will be removed from one alcohol molecule and it will lead to the formation of alkene. So that is the side reaction, which can also take place under the same condition, but that is not the desired reaction. So only when the starting alcohol, for example here we have taken methyl alcohol, ethyl alcohol, when these alcohols are very simple in nature, that is the alkyl group that is present in alcohol is very simple, then only ether formation will be, that will be the major product, not the alkene is major product here. But suppose if the starting material, that is the alcohol, in the alkyl group there is some branching present, so now there will be chance of this side reaction, which is unimolecular dehydration. So see, this is the example. Here unimolecular dehydration you can find in case of isopropyl alcohol. So here the group is CH3, CH, in the middle carbon there is OH. So this is 2 degree alcohol. Fine, you can also write it in this way, Me2CHOH. So this group is basically isopropyl group, and under same condition, only the temperature is a little bit high, there is removal of water, one water molecule. So here we have taken single molecule of isopropyl alcohol and you are getting propene, because this OH is removed along with hydrogen from any of this methyl, because this is symmetrical structure. Ultimately there is formation of CC double bond and removal of water. So in this case ether is not formed. Fine. So this reaction is, if you want to use this reaction for formation of ether, you can, there is some limitation, and the limitation is only when the alkyl group is very simple, primary alkyl group, then only you can use this reaction for formation of ether. But if there is some branching or if the alkyl group is not so simple, then there will be formation of alkene, but that is not the desired reaction. Okay, so this is the limitation of this reaction. And one important application is that by this bimolecular dehydration you can make commercially diethyl ether. So basically it is this reaction, diethyl ether you can make starting from two molecules of ethyl alcohol, and this is a commercial method for production of this diethyl ether. That means large scale production is possible by using this bimolecular dehydration method of alcohol. So here you have to start from two molecules of ethyl alcohol in presence of H2SO4 and 140 degree centigrade. Okay. Next method is Williamson ether synthesis. So this method is basically the most versatile method for making ethers. So in the last method you have seen formation of symmetrical ether, right? Both sides of the oxygen there is same group, methyl group or ethyl group. But in this case you can make unsymmetrical ether also. Fine. Now two reaction partner is present in this Williamson ether synthesis. One is alkyl halide, that is Rx, that is the general expression of this molecule. Another reaction partner is metal salt of alkoxide, metal salt of alcohol, which is basically known as alkoxide. So how you can make it? You have to start from the corresponding alcohol, which is R prime OH. Now if you remove this H with sodium, that is now it is sodium salt of the alcohol R prime OH, then it will be called sodium alkoxide. Similarly, if you have used KOH, that is potassium hydroxide, you will get R prime OK. So whatever is the metal, here the important thing is negative charge is present over oxygen. So it is called alkoxide. Now alkoxide, the term is coming from alkyl. But suppose if the alkyl group, that is if this R prime group, if it is methyl, then it will be methyl O minus, that means it will be methoxide. See, this is the general expression. Now if it is methyl, it is methoxide, that is ending with IDE. If it is ethyl, it is ethoxide. If it is isopropyl, it is isopropoxide, like this. So one reaction partner is alkyl halide, another reaction partner is alkoxide. Fine. So it uses alkoxide ion, that is R prime O minus ion, to attack alkyl halide, substituting this the alkoxy group for the halide. So here R prime O minus, that can attack this R group, and this halogen, it will be removed in the form of halide. Now it can bind with Na plus, and ultimately it will be removed in the form of NaH. So suppose if it is Cl, it will be NaCl, and you are getting ether, where one side you have R group which is coming from alkyl halide, another side we have R prime which is coming from the alkoxide part. So as if, let me erase all this. So if you look at the product and starting material carefully, as if it is replacement of X by OR prime group. Fine, that is a substitution. Now it follows SN2 mechanism. So as it is, it follows SN2 mechanism, and we know that for SN2 alkyl halide that we take, that must be very simple. It is either primary or methyl. So methyl and primary halides are the excellent substrate for this Williamson ether synthesis. So this is a general equation, but if you consider actual equation, see here we have taken methyl iodide CH3I and sodium ethoxide. So the corresponding alcohol, that is ethyl alcohol, from which you can make this ethoxide CH3CH2O minus. This is plus. Now if you are thinking why we cannot use directly the alcohol, that is why we are not using directly the ethyl alcohol. The reason is, if you are using ethanol, that is ethyl alcohol, better I give the explanation in terms of the general equation. Suppose if you use R prime OH rather than R prime O Na. Now the thing is, here lone pair is basically attacking, but if you have taken alkoxide, there is actual negative charge present. Obviously its nucleophilicity is higher compared to the oxygen in alcohol. So that is why alcohol must be converted to alkoxide, and then this SN2 mechanism is better, because now it can act as beta nucleophile. Okay, so that is why we take alkoxide. So here we are getting ethyl methyl ether. So this methyl part is coming from methyl halide, that is iodide, and this ethyl part is coming from ethoxide. Fine. Now we know that this alkoxide, that is R prime O minus, they are actually very strong base. So when it is acting as nucleophile, then you are getting ether as product, because here SN2 is the mechanism, substitution. So in substitution, R prime O minus, it is basically attacking, that is this CH2CH2 minus, it is attacking carbon. So now it is behaving as nucleophile, but the same species can also act as base, and when it is acting as base, obviously it will now capture some acidic hydrogen, but that will not lead to the formation of ether, because that will not lead to substitution mechanism. Now it will be elimination. So alkoxide, as they are also strong bases, so there is a chance of competition with elimination reaction by E2 pathway. So that is one disadvantage of this reaction. So E2 path, that is elimination reaction, that will be very major reaction if the alkyl halide it is sterically hindered. That is, instead of taking methyl or 1 degree halide, suppose you have taken 2 degree halide or 3 degree halide, then this chance of elimination is increased. Okay, because for SN2, first of all, methyl and primary halides are based, and when it is 2 degree 3 degree, that means already some steric hindrance is present in the alkyl halide, and it will try to get rid of this extra steric hindrance, and that is possible if you are removing some small molecule HX, that is hydrogen halide, and in that case alkoxide is behaving as base. Fine. So that is why if the alkyl halide, that is this Rx, if it is 2 degree or 3 degree, chance of elimination is increased. Here we will see two options to prepare isopropyl ethyl ether. Now isopropyl ethyl ether means on one side of oxygen there will be isopropyl group, that means Me2CH, another side there will be ethyl, that means CH2CH3, right? So this is actually the structure of isopropyl ethyl ether. Now this you can make by taking two types of combination. In one combination, see, we have taken ethoxide ion and isopropyl chloride. Fine. So now this is acting as nucleophile. It is attacking this carbon which is containing chlorine, and ultimately there is, sorry, this is not R, this is CH3. There is formation of isopropyl ethyl ether. Another combination that is possible, that is the reverse. Now ethoxide, not ethoxide, now the alkoxide is coming from this one, that is diisopropoxide, because this is isopropyl group and oxygen O- is attached to middle carbon, so this is isopropoxide, and the alkyl halide is now 1 degree, not 2 degree. So this is now attacking, and you are getting again the same molecule. Now as this is 1 degree, that is the second combination. Suppose this is number 2, this is number 1. Now the second combination is better, not this one, because in the first combination, as the alkyl halide is 2 degree, so not just substitution product, this is substitution product because it is ether, but elimination product will also be there, and elimination basically will predominate. Fine. But if you have taken the other combination where the alkyl halide is 1 degree, in that case, as it is less hindered halide, so E2 will not predominate, and that is why it is the preferred path. So suppose if this type of molecule is given and it is asked that which combination is better, you have to check that which combination to take. That combination where alkyl halide is very simple, either methyl or primary, not 2 degree or 3 degree, because whenever it is 2 degree or 3 degree, there is a chance of elimination reaction, which is obviously not desired. Fine. Limitations of these reactions, that is Williamson ether synthesis. Secondary alkyl halide can compete with elimination. So secondary alkyl halide we cannot take, and if heat is applied, however, E2 will be most likely predominate. So when you have taken secondary and heat is also applying, we are applying, then chance of elimination is even increased, because higher is the temperature, higher will be the chance of elimination. So this is the problem, and if it is tertiary alkyl halide, it fails completely in Williamson. So with 2 degree, there is a chance of getting ether, maybe it is in less percentage, but still there is a chance. But if it is tertiary, it is failing completely. Fine. Also, not just secondary alkyl halide or tertiary alkyl halide, suppose the base that you are using, that is alkoxide, if it is very bulky and if it is very strong, now there is also problem of elimination. So suppose the alkoxide you have taken is isopropoxide, that is Me2CHO-, or if you have taken tertiary butoxide, fine, TBUOK. So tertiary butoxide is basically this molecule, 3 methyl group, then O-, K+. This is a very strong base. Not only it is a strong base, but it is also hindered, right? And Me2CHO minus, that is isopropoxide, where we have 2 methyl, 1 hydrogen and O minus. Fine. So these two are very strong base, and also they are very bulky. There is steric hindrance. So what will happen if you are using this type of alkoxide? That will also favor the elimination pathway. Okay. So not just, you don't think that if you have taken 1 degree alkyl halide, then your problem is solved. No. The base, what kind of base you have taken, that also you have to take care of. So if the base you are using is very bulky and very strong, then also there is a chance of elimination, because now this alkoxide, rather than acting as nucleophile, our purpose is that this strong base, this alkoxide, it should behave as nucleophile, then only ether you can get. But if it is behaving as base, not nucleophile, then the problem will arise, because when it is base, rather than acting as nucleophile, now it will capture hydrogen. Okay, but that is not wanted, and when it will capture acidic hydrogen, there is a chance of elimination. Okay, so same species actually can behave as nucleophile as well as it can behave as base, because both are electron rich species. But remember, there is a difference. When we are calling it nucleophile, basically the negative charge is attacking electron deficient carbon. So for example, the carbon of the alkyl group in alkyl halide. But if it is behaving as base, it will capture H, because that is the property of base. So this is the difference between nucleophilicity and basicity. Both are carrying some negative charge, but there is difference depending on where it is attacking. Nucleophile will attack electron deficient carbon and base will attack acidic hydrogen. Fine. So here we have these two equations where the alkyl halide is 1 degree, but the base you have taken is tertiary butoxide, which is bulky and strong. So what will happen now? It will capture this beta hydrogen. Why I am calling it beta hydrogen? Because with respect to bromine, this position is alpha, this position is beta. So beta carbon, the hydrogen that will be attached to beta carbon, that will be called beta hydrogen. So it will capture this hydrogen. As a result, CH bond will be broken, there will be CC bond formation, Br will be removed. So ultimately you are getting alkene. But this is elimination product. But if it is behaving as simply nucleophile, so if it is behaving as nucleophile, then it will attack this carbon and Br will be removed. So this is SN2 product, which is ether, and if it is E2, then alkene is the product. But unfortunately here the elimination product is major. Fine. But suppose if the alkoxide you have taken, it is not bulky, and see here it is not very strong base. Why? Because here you have 3, that is more is the number of methyl group. Because of electron donating capacity, negative charge density will increase, but that is not the case in case of ethoxide, and also it is not bulky. So now mostly substitution will take place and you will get ether as the major product, because here SN2 mechanism is major and E2 will be minor. So here the solution of this problem that you can consider, one way to attempt to get SN2 to be favored, because our purpose is to get SN2 product, which is ether. So for SN2 to be favored over E2, what you can do, you can use polar aprotic solvent. Now when you are using polar aprotic solvent, it will increase the nucleophilic character of the alkoxide. Now how it is increasing nucleophilic character? So suppose the alkoxide is R prime O minus, fine, and if you are using polar aprotic solvent means no active hydrogen is present. Active hydrogen means hydrogen if it is attached to electronegative element. Suppose hydrogen attached to oxygen, for example in water or any alcohol or acetic acid, this type of solvents when you are using, it is they are basically polar protic solvent. And polar protic solvent, they have this property that by hydrogen bond formation with this O minus, they can stabilize by solvation, they can stabilize this alkoxide. So as a result, its nucleophilic character will decrease. But when you are using aprotic solvent, this type of solvation effect is not possible. So R prime O minus, that is alkoxide, it will be comparatively in free nature, free condition. And when it is in free condition, obviously its nucleophilic character will be high. So that is why by using polar aprotic solvent, you can get SN2, that is, you can make this reaction to be favored for SN2. Okay. Next point, haloadding. So until now, all discussion that we are doing, it is basically formation of ether, and where both side the alkyl groups are aliphatic. But suppose if you are making aromatic ether means one side there will be R group, but another side there will be aryl group. If it is simply benzene ring, it is pH, but if there is some substitution, it will be better you write the general expression aryl, AR. So for the preparation of aromatic ether, one possibility is that you can use haloarine, just like you have used for formation of aliphatic ether, you have used alkyl halide. So for formation of aromatic ether, you can think that I will use ARX, that is haloarine, but haloarine cannot be used for preparation of aromatic ether because of partial double bond character of the carbon halogen bond. Fine. So here, if you want to make ROAR, that is aromatic ether, then which combination you have to take, that is very clear here. You cannot take the combination where one reaction partner is ARX, another one is RO minus. This combination is not right, okay, because of this double bond character between carbon and halogen. So here if we want to make this ether, that is phenyl methyl ether, then the first combination, possibility A, you have taken phenyl bromide and methoxide, sodium methoxide. Possibility B is now you have taken sodium phenoxide, that is sodium salt of phenol and CH3Br. Now this combination is correct, not this one. And why? Because now you have used haloarine. So the problem with haloarine is that here resonance is possible with the double bonds of benzene ring. So now see, there is a double bond character between halogen and carbon. Halogen is positively charged, negative charge is here. Now further resonance structure also you can draw, and you will see in all this resonance structure there is partial double bond character between carbon and X. Now when there is double bond character generation is taking place and the O negative is attacking here, the breaking of this CBr bond, it is very difficult, because to break a double bond compared to single bond, obviously it is difficult process. So that is why you cannot take that combination during the preparation of aromatic ether where haloarine is one of the reaction partner. So this is not the correct possibility. The second possibility is actually the correct combination. So based on this Williamson ether synthesis, we have a question here which is assertion reason type of problem. Now here the statement in assertion is saying that synthesis of ethyl phenyl ether. So one side you will have pH, another side we will have ethyl group. For formation of this type of ether, which is basically aromatic ether, may be achieved by Williamson synthesis. Now obviously this is true, because by Williamson synthesis we can make unsymmetrical ether. But the question is, what combination you should take? So in the reason it is saying that reaction of bromobenzene, that is PHBr, with sodium methoxide, that is ETO minus Na plus, that can lead to the formation of ethyl phenyl ether. But remember in the last slide what we have seen, you cannot use haloarine, and here PHBr if you use, there will be double bond character present between bromine and the carbon with which it is attached. So because of this double bond character, the breaking of this bond is really difficult. So you cannot take this combination, right? So here the statement in assertion is fine, because we can make this by Williamson synthesis. But the combination that is given in the reason, the statement in the reason, that is actually not correct. So which combination we should take? We should take sodium phenoxide, not sodium ethoxide. So for the ET part, that is one side you have ET, so you have to take ethyl bromide. Okay. So the problem with bromobenzene is that there is partial double bond character present. So this is not the correct combination for the formation of phenyl ethyl ether. So here the first statement is correct, but the second statement is not correct. So that is why option 3, that is the correct option. Okay. So after finishing preparation methods of ethers, next we will see physical properties of ethers. Now the first point under physical property is dipole moment. The presence of an electronegative oxygen atom in ether, it gives them a small dipole moment. Okay, so look at this structure. We have taken the general ether structure ROR. Now as oxygen is more electronegative, the direction of this dipole moment, that will be towards oxygen. This is also same. So there is small amount of dipole moment present. So if you take actual example, we have taken dimethyl ether where dipole moment value is 1.3 dB. Okay, and overall dipole moment direction, see, this is towards this side, because individual dipole moment of carbon oxygen bond, if you consider, this is the direction and this is the combined effect. Okay, the weak polarity of ether do not appreciably affect their boiling point. It is true that there is some dipole moment, but that is not very high. There is polarity, but the polarity is not very strong, it is weak. So because of this type of weak polarity, there is not much effect in the boiling point, because if the polarity of this bond is very high, then interaction between these molecules will be high, and as a result, to separate them, boiling point high means what? You are changing the physical state from liquid to vapor. Now from liquid to vapor means you have to separate the molecules from each other, but that process will be very difficult if this one polarity is very high. So here, as it is weak, it has not much effect in the boiling point. Okay. Next point is solubility. Solubility of ethers. Ethers, when it is containing 3 carbon atoms, that is total number of carbon atoms, suppose it is up to 3, then under this condition we can say they are water soluble because of hydrogen bond formation with water. So see, this is ether molecule and 2 molecules of water, hydrogen bond formation with the H of water and oxygen of ether, another water molecule on the right hand side. So this type of hydrogen bond formation is possible, and that is responsible for their solubility. But solubility decreases with increase in the number of carbon atoms. Okay, suppose the number of carbon atoms, if these are group, when it is beyond 3, now it will make what it will do, the hydrocarbon part of the molecule is very high now. So as a result, as the hydrocarbon part means what? It is a non-polar part. There is no electronegative atom, right? So non-polar part when increased compared to the polar part, obviously now the solubility will decrease. Ethers are appreciably soluble in organic solvents. So except water, if you consider solubility in other solvents, that is in some organic solvents like alcohol, benzene, acetone, they are appreciably soluble. Boiling point, which is basically related to the dipole moment. See, here we have taken N-heptane. So total number of carbon is 7. Then we have taken 1 methoxypentane. So one side of ether there is methyl group, another side we have pentane. That means total 5 carbon. Okay, and the third molecule, it is hexane 1-ol. That means 6 carbon chain, linear chain. Then there is OH. But why we have taken these molecules? See, their molar mass are very close to each other. Look at the molar mass value of all these molecules. They are more or less same. So when molar mass is more or less same, you can expect boiling point to be same. But here there is drastic difference when you are moving from this hydrocarbon N-heptane, which is having 371, and now you are having ether. Both are actually having almost same boiling point. But when it is alcohol, molar mass is same, almost same. But look at this change of value. Now it is 430. Fine. So we can say that when you have alkane, ether and alcohol, these three types of molecules having more or less same molar mass, that is molar mass value very close to each other. Under this condition, the boiling point of ether is comparable to the alkane. So these two are having almost same boiling point, but it is not comparable to alcohol. So ethers have much lower boiling point as compared to isomeric alcohol. Fine. So why I am calling it isomeric? Because here you have one methyl group, one carbon, this is 5 carbon, total number of carbon 6, and here also total 6 carbon. So you can say it is isomeric alcohol. So compared to this alcohol, isomeric alcohol, their boiling points are much low. So in this way we can compare boiling point with alkane and alcohol. After physical properties, next we will see chemical properties of ethers. The first chemical reaction for ethers, cleavage of carbon-oxygen bond. So we know that in ether you have carbon-oxygen bond. And how the cleavage is possible? When excess of hydrogen halide is added to the ether molecule, cleavage of CO bond takes place, leading to the formation of alkyl halide. So here we have taken the ether ROR and hydrogen halide HX we have taken. So what reaction we are getting? We are getting this R is now attached to X. So this is alkyl halide, and this OR that is now attached to H. So you are getting alcohol. Now the order of reactivity of hydrogen halide, that is what type of hydrogen halide you have taken, depending on different halogen atom. It may be HI, HB or HCl. So when it is HI, the reaction rate is high, then gradually it will decrease when you are moving to HBr and then HCl. If you are using excess of hydrogen halide, that is suppose you are using excess of HBr or HI, then the alcohol formed, it can further react with this excess HBr or HI to form alkyl halide. Here we have this general reaction. ROR, first it will react with one molecule of HX, it will form ROH and RX. But as you have used HX, that is hydrogen halide, in excess, so it can again further react with HX, another HX molecule, hydrogen halide, and it can form now this R and X together, it is making RX, and water will be removed. So depending on whether it is you are using ROR and HX in 1:1 or you are using HX in excess, depending on that, product will be different. Now this example that you have seen here, it is symmetrical ether. But if you have used unsymmetrical ether, now what will be the nature of product? Fine. If an ether does not contain a tertiary alkyl group, so when it is unsymmetrical ether and under that condition, suppose in the ether molecule there is no tertiary alkyl group, then what will happen? Then the halide ion always attack the smaller alkyl group by SN2 mechanism. Here we have taken the unsymmetrical ether where one side you have methyl group, another side you have ethyl. So among these two groups, which one is smaller alkyl? Obviously methyl. So now what product combination you will get? You will get iodomethane. So the halide that will be generated, that is actually with the small alkyl. So you will get iodomethane and ethanol, not the other combination, that is CH3OH and CH3CH2I, that you will not get. Fine. Because here as it is SN2 mechanism, so this I minus, it will always prefer to attack the small alkyl group, and this O CH2CH3 this part will be removed as if it is the leaving group. Remember the mechanism of SN2? The nucleophile, it attacks the carbon and leaving group is removed. So here leaving group is OCH2CH3. Fine. Another example, again we have taken an unsymmetrical ether where one side we have methyl group, another side we have isopropyl group. Now among these two, which one is smaller alkyl group? Obviously the methyl group. So here Br minus, that will prefer to attack this methyl group and this carbon oxygen bond will be broken. So the alcohol that you will get, that is isopropyl alcohol, not methyl alcohol, and the halide will be CH3Br. So in this way, when it is the starting material is unsymmetrical ether, then this should be the product combination, not the other one. But provided it is true only when there is no tertiary alkyl group. Some more points under this heading, that is products in case of unsymmetrical ether. If an ether contains now a tertiary group, now what will happen? Now the halide ion always attacks the tertiary alkyl group and it is now by SN1 mechanism. We know that for SN1 mechanism 3 degree alkyl halide is base, though here it is not 3 degree alkyl halide, but here this OCH3, that will behave as the leaving group. Okay, so better I write it in general, R, that is some alkyl group attached to leaving group. You are using halide, which is the nucleophile here. So this R minus, it will attack, Lg will be removed. So in our case, this is actually Lg, right? And we know that SN1 mechanism, it is always good for 3 degree. So that is why this I minus, that will attack this carbon and carbon oxygen, this carbon oxygen bond will be broken. CH3O minus, which will capture this H, ultimately it will form alcohol. So now the alkyl halide that you are getting, that is basically from the tertiary part, and the alcohol that you are getting, that is from the other part. Next point, if one of the R group of ether is phenyl, now under this condition the products formed are always phenol and alkyl halide. So you will never get PHX, that is phenyl halide, that you will not get. You will always get phenol, and from the other alkyl part you will get the alkyl halide. So here we have this aromatic ether, methyl phenyl ether. So here I minus, that will attack this CH3, this carbon oxygen bond will be broken. Okay. So the I minus, it is not that the I minus it is attacking this carbon. No, that is not possible. Now question may arise, why one of the product is always phenol? So this question is for the second point. There is some double bond character present between the benzene ring and the ethereal oxygen. So if I write the same molecule OCH3, there is double bond character present because of this type of resonance. Negative charge, OCH3, oxygen is positive. So see, double bond character is present between carbon and oxygen because of this resonance. In further, if you draw the other resonance structure, then also double bond character is present. So as there is double bond character, it is difficult to break it, and that is the reason diphenyl ethers do not react with HX. So in this case, one side you have methyl, another side you have phenyl. But suppose both sides, if there is benzene ring, then what will happen? So benzene ring attached to oxygen, another benzene ring. Now both sides there will be some double bond character between the oxygen and carbon. So for this type of molecule, that is diphenyl ether, or better I say in general ARO, that is if there may be any substitution in the phenyl ring. So for this type of molecule, reaction with HX is not possible. So at least on one side there should be some alkyl group, then only cleavage by HX is possible, otherwise it is not. Now after this first chemical property, which is cleavage with hydrogen halide, the next reaction is peroxide formation. Many ethers can react with atmospheric oxygen, that is oxygen that is present in atmosphere, forms explosive hydroperoxide and dialkyl peroxide compounds by free radical mechanism. So for example, see, we have taken diethyl ether, you can also call it ethoxyethane, and in presence of excess oxygen, which is basically coming from air. So sometime in question it may be that oxygen is not written, simply air is written. So it actually means the same thing. Now what will happen? Two types of reaction possible. Any of this hydrogen, that is the hydrogen which is present in the adjacent carbon of oxygen, it may be replaced by this OOH, and this molecule is known as hydroperoxide. Fine. Peroxide is this molecule, HOOH. So as if here this part is attached by removing this hydrogen of these CH2 groups, and we are getting 1-ethoxy-ethyl hydroperoxide. 1-ethoxy, why we are saying, so this is ethoxy group, 1-ethoxy, so as if it is number 1 carbon if you consider. So at number 1 carbon there is ethoxy, so that is why 1-ethoxy, and itself it is 2 carbon, so ethyl, but there is also hydroperoxide group at 1 position, so that is why ending with hydroperoxide. And another possibility is formation of dialkyl peroxide. Now peroxide, when we are saying, it is basically OO linkage, and there may be any group both side. So here both side we have ethyl group, so as if here one more oxygen is inserted, and that is diethyl peroxide. So in presence of atmospheric oxygen, or that is the oxygen from air, this type of reaction possible by free radical process. Third reaction, electrophilic substitution in aromatic ethers. So these third chemical properties that we are going to discuss, that is actually only for aromatic ethers, not aliphatic. So there must be one aromatic ring on one side. The alkoxy group, that is OR, O-alkyl group, is an ortho-para directing group as well as activating group. So when we are saying aromatic ether, basically pH ring or substituted pH ring must be there, and also there is oxygen and some alkyl group. So as if here OR group is attached to any of this carbon of benzene ring. Now this group, that is alkoxy group, simply you can take OMe group. This is donating group, it has plus R effect because of this lone pair over oxygen. So this is activating the benzene ring, and when it is activating the benzene ring, it will be orthopara orienting. And orthopara orienting means if you are using some electrophile, the electrophile will enter only at the ortho position. These two are ortho position or para position. So that is why it is electrophilic substitution reaction. Electrophilic substitution reaction means the reagent that you will use, that will contain some electrophile, and that electrophile will replace any of these orthohydrogen or parahydrogen. So ultimately the product that you will get is OR, and if I am writing the ortho product, orthohydrogen replaced by E, and the para product, it will be like this. So mixture of these two depending on major and minor, that depends on the actual structure. So this is example of electrophilic substitution reaction in aromatic ethers. It activates, that is the OR group activates the aromatic ring towards electrophilic substitution because the reagent itself is electron deficient, and OR group is donating because of its plus R effect. So it will increase the electron density of benzene ring. So as a result, the reaction between E plus and the benzene ring, that will be highly facile. It activates the aromatic ring towards electrophilic substitution in the same way as in phenol. because in phenol there is OH group, not OR, but that is also activating an orthopara orienting. Some examples are halogenation, that is halogenation of aromatic ether. So suppose if you take simply PHOMe, after halogenation, if you are doing the halogenation with bromine, there will be insertion of bromine to ortho and para. If you are using doing nitration, that means electrophile is now NO2 plus, NO2 will be inserted in ortho or para position. If it is Friedel-Crafts reaction, Friedel-Crafts may be Friedel-Crafts acylation or Friedel-Crafts alkylation. So if it is alkylation, some R group will be inserted in ortho and para. If it is acylation, that is Friedel-Crafts acylation, some acyl group will be inserted in ortho position or para position. Okay. Now we will see the reactions one by one under electrophilic aromatic substitution. So when it is halogenation, anisole, which is basically methyl phenyl ether, this molecule is known as anisole, undergoes bromination. Now you are using bromine as a halogen, so that is why we are calling it bromination. With bromine in presence of acetic acid and absence of catalyst. So you don't have to use any catalyst separately, because OCH2 group is already donating group. Catalyst is normally required when the ring is not so much activated, but if the ring is already activated because of this presence of OMe, so obviously you can do this even in absence of catalyst. So major product is para-bromo because of steric hindrance, but both ortho and para will be formed. Friedel-Crafts reaction. So Friedel-Crafts reaction we are doing, we have taken here the reagent CH3Cl, here the actual electrophile is methyl plus. You have to use some anhydrous AlCl3 as catalyst. So this catalyst is basically Lewis acid. It will help to generate this electrophile by removing this Cl. Now see, this R group is inserted either at ortho position or para position. And this is the major product, again because of steric problem of ortho product. So this is 2-methoxytoluene, because toluene is methyl substituted benzene. And at 2 positions, so this is 1 position, this is 2, and this is 1 position, this is 4. So one is ortho product, we are calling it 2-methoxytoluene. The para product we are calling it 4-methoxytoluene. So this is example of Friedel-Crafts alkylation, because alkyl group is inserted. And the second one, acylation. So when it is acylation, same catalyst you have taken, but rather than taking Rx, this is Rx, now we have taken RCOX, acyl chloride, and COCH3 group that will be inserted either at ortho position or para position. This is again the major product, and this is called 2-methoxyacetophenone, because acetophenone is basically PHCOCH3. So as if it is 1 carbon, this is 2, so this is 2-methoxyacetophenone, this is 4-methoxyacetophenone. Fine. So these two are the examples of Friedel-Crafts reaction, alkylation and acylation. And nitration reaction. So for nitration reaction, here the electrophile is NO2 plus, but this electrophile is generated when you are using mixture of concentrated H2SO4 and HNO3. So this electrophile is now inserted either at ortho position or para position, and para is major. So these are the 3 important examples under electrophilic aromatic substitution. Uses of ethers. What we can do with ethers, that is application. So in medicine, it can be used as anesthesia and antiseptic, as solvent in the laboratory, as they are very unreactive in nature, because they are very weak polarity present, so they are not very reactive. So that is why they can be used as solvent, because if a molecule is very reactive, you cannot act as solvent, because when you are doing some reaction in solvent, we want the solvent just to act as media. We do not want the solvent molecules to take part in reaction, right? So solvent must be unreactive. So as ethers are unreactive, you can use them as solvent. Solvent for what? For oils, fats, resin, wax, perfumes, because all these molecules are soluble in ether. Their ability to form hydrogen bond and combined with the weak London forces of the alkyl group that are bonded to the oxygen, this property makes ethers a good solvent for wide range of organic compounds. So they can form hydrogen bond because of the presence of oxygen, and also there is some alkyl group present, and when nonpolar alkyl group is present, weak London force is also present. So here you can see both polar region and non-polar region both are present. So that is why they are very versatile when the question of whether they can act as solvent or not. So as solvent their application is very versatile. Here we have some examples of solvents. Diethyl ether, that means ethyl or ethyl. This is a very common solvent. Its boiling point is very low, around 34 degrees centigrade. So if you are doing any reaction at very low temperature, that is you are not heating it, then this solvent is very suitable. Tetrahydrofuran. Furan is this molecule. But suppose if you are removing this unsaturation, now it is like this. So this molecule is tetrahydrofuran. Why tetrahydro? Because 4 hydrogen atoms are attached, so that is it is tetrahydro. Here you do not have any CC double bond, and in short it is called THF. So sometime we will see some reactions are written on the arrow, there is written THF. So it means tetrahydrofuran is used. Now this is a cyclic ether, you can understand from the structure. Then dimethoxyethane, DME, DME. So this is another important ether. Then we have 1,4-dioxane. Dioxane is basically cyclohexane with 2 oxygen, but when we are saying 1 and 4, that means this should be the position of oxygen. So this is also cyclic ether, and 2 ether groups are there, right? So this is also another important examples for ether solvent. As perfuming and flavoring agent, ethers are widely used in perfumery industry, aroma industry, because they can provide flavors to a variety of food and drugs. For example, methoxybenzene, that is anisole, that we have just discussed. PH, OCH3, this is anisole or methoxybenzene. It is commonly used as a constituent to impart fragrance. In paints, ethers are used in dyes and paint industries also. Okay, so here you can see different application methods for ethers. Multiple correct choice question. Here the question is saying that which among the following statement, or it may be statements plural, about ethers is or are correct. The first option is peroxide is obtained in presence of air. Remember the reaction that we have seen when you are treating any ether in presence of excess oxygen, that is environmental oxygen, which is basically presence of air. Then you get 2 types of compound. One is peroxide. Just have a look here. This reaction I am talking about. So in this case, when you are using atmospheric oxygen, or you can say air, hydroperoxide generated and also peroxide generated. So this statement that is given in the question, this is obviously correct. Peroxide is obtained in presence of air. Now the second option, ethers are weakly acidic. Ethers are having structure either ROR or ROR prime, that is unsymmetrical. But you cannot see any acidic hydrogen. That is weakly acidic means there must be some acidic hydrogen, because here hydrogens are attached to carbon in the alkyl group. There is no such hydrogen directly attached to oxygen. So we cannot say there will be any acidic property. Fine. Then ethers form oxonium salt. Oxonium salt means oxonium ion, remember H3O plus, we say it is oxonium. That means oxygen must carry some positive charge. So here if this oxygen is protonated like this, there will be positive charge generation, right? So this is possible. Ether forms stable complexes with Lewis acid. Lewis acid means there are different types of definition possible for acid. Now protic acid means which is having active hydrogen, for example HCl or HBr. But there is another type of acid which is basically electron deficient, and they are always searching from some electron density. So the molecules that can accept electron pair, that will be called as Lewis acid. Very good example is AlCl3, because this is its octet is not complete, so it is electron deficient. It can behave as Lewis acid. Now ethers, as there is presence of oxygen and there is lone pair, so it can donate lone pair towards Lewis acid, so stable complex formation is possible. So here except B, all these other statement A, C, D, all are correct, that is about ethers. Okay, so A, C, D, these will be the correct option. Next question, which of the following ethers will get hydrolyzed by HI? Remember the chemical properties when we have discussed. The first reaction is cleavage of ether with hydrogen halide, and for that purpose HI is very good substrate. Now if you look at these 4 ether molecules, this is containing benzene ring both sides, so it is not possible at all. Then in option D also, one side you have benzene, another side you have derivative of benzene, because this is also benzene, only difference is OMe is there, but still it is aromatic group present both side. But C and D, C and B, if you consider, there is only one side there is benzene ring present. Okay, but as we know that when there is aromatic ring present, double bond character is there. So that is why when both sides you have aromatic ring, cleavage by HI is not possible. But option B, one side there is no such thing. So you can expect that here I minus can attack this carbon. But actually see, this is very hindered carbon. Fine. And if you consider option C, though option B and C both are having same kind of structure, but here it is completely strained because it is locked. But here these 3 ethyl groups, they are free in nature. So attack of I minus, that is when I minus will try to reach this position, it is comparatively easier when it is C rather than B. Okay, so this is also not possible. And in this case, that is option D, which of the following ethers will get hydrolyzed by HI? So here at a first glance it seems that both sides there is benzene ring, but see, this OCH3 is also containing an ethyl linkage, right? So as if I write the molecule again, PHO, then OCH3. Here if you are focusing this oxygen as ether, then it is not possible. But suppose if you are focusing this oxygen as ether, one side you have this group, another side there is CH3, so I minus can easily attack on this carbon, so you can get hydrolyzed product. So that is why, both option C and option D, this will be correct. But attack of I minus towards this carbon, it is really difficult process, so that is why it will not be the correct option. C and D, these 2 are the correct option. So more problems are there related to ether that we will discuss in the next class. So for today we will end here. So thank you for listening. We are ending the session here.